Welcome to a lesson with Dr. Powell. Let's show that if we have an undirected graph, we're just assuming it's undirected, and in particular it's finite, has a finite number of vertices and edges, that if the degree of every vertex, that means how many edges each vertex touches, is even. So the degree of vertex is even for all the v in the graph. Then if we remove one edge, just one edge, the graph will still be connected. All right. So how are we going to do that? Well, let's take a look at this and think about this on the incidence matrix for a minute. If we were to make an oriented incidence matrix here, think about what's happening in every column, you'll have a -1 and a 1 somewhere. And if you look across a row in that incidence matrix, it's going to represent a vertex. And every time, if the degree of a vertex is even, then what happens is, let's see, with each edge touching it, so with each edge that touches it, you'll get a 1 or a -1 from it. So you're adding up lots of 1s and -1s. Now, a sum of 1s and -1s doesn't change from being odd to even when you change up the minuses or the pluses, because mod 2, -1, is actually equal to 1. They're equivalent mod 2. So really, another way of saying that this is even is saying that the sum of each row is even in the incidence matrix. Okay, so we're going to use that idea that that we require that every row has to be, so the sum of each row has to be even in the incidence matrix. Okay. Now, it is true, though, that that at worst you have to have an even number of rows that have an odd sum. I mean, in our particular case, we're going to make this assumption, but in general, we have to have an even number of rows. Like if we actually start to kind of mess around with this a little bit, we might need this fact here. In any undirected graph where you have an oriented incidence matrix here, it's oriented, so you have -1s and 1s, so you actually make some directions for it. But if you look at it, there has to be an even number of rows that have an odd sum. Let's see why that is. Well, for one, I mean, the sum of all the entries in the incidence matrix has to be even, because each column has two things in it, 1 and -1, and sum is 0. I mean, the sum of everything is 0, which is even for sure. Sum of everything is even. So if there were an odd number of rows with an odd sum, so you're adding up an odd number of odd numbers, you actually end up getting something that's odd. Then you end up adding that to something that's even. You're going to get something that's odd, but we require that everything's even, which means like the sum of everything, of every entry in here together has to be even. So that means, and we can conclude that we can't have an odd number of rows with an odd sum. It always has to be even. So we'll just put that off the side and use it in a minute. Okay, so really our assumption that the degree is even, we can disguise this way by saying the sum of each row in the incidence matrix is even. All right. Now, when we remove one edge, let's see what happens. So if we remove just a single edge from here, what could happen is we're removing a -1 and a 1 out. And let's suppose that it makes the graph disconnected. That means it would make another component. So you would make so if you remove this edge in here. Okay, so removing this from being connected to that. This is still connected to everything it was connected to, and this is still connected to everything it was connected to, but these are just not connected to each other. The worst case is we just have two components here. So this -1 and 1, if we remove it and we make two components, let's see what's happened. One of these vertices actually is in one component. This vertex is actually in the other component. So we've actually changed up one row to have an odd sum because we took a 1 away from it. And if it's in one component by itself, we could have an incidence matrix, and let's just assume it's over here. An incidence matrix for over here. And if you remove one thing from it, and here you move one thing from it, so what you have is you have a row that has an odd sum. And over here, you have a row that has an odd sum. Also, since they're connected components, notice that this row over here will have no entries in the other place over here, because these vertices won't be connected to anything that we're connected to over here in this other incidence matrix. Similarly over here. So really, each row if you have two different connected components, can be split up into a place in one incidence matrix and the other. So if it's an even sum, it'll be an even sum in just one of the in both of the components, because it's either going to be 0 or whatever it is in the other one. So we have and so what's actually happened is, if we looked at both of these connected components, we've actually produced exactly one odd sum row out of all of them. The rest are still even, and similar for the other one. Well, that contradicts this fact that we have to have an even number of rows with an odd sum, which actually guarantees that we cannot, if we take one column away or one edge away, the graph will still be connected. We won't have those two. So this is a proof by contradiction. So the graph is still connected when we remove just one edge. Thanks for watching.